Okay, I'm ready.
All right, so our next speaker of the day is Jean-Marie de Konick from Université Laval, and he will tell us about construction of normal numbers using the factorization of integers. Please go ahead.
Okay, thank you, and thanks Florian and Claude for inviting me for this session. Some of you are familiar with normal numbers. Those that are know that it's a fascinating subject because we don't know much about them, and at the same time we know very much. So that's what I will be talking about. So first of all, the definition, if we start in a given base Q, with normal number is an irrational number, and it's called a Q normal number if when you look at the its infinite expansion of digits, if you take any given sequence, say of 3 digits, then it occurs as the same frequency as any other sequence of 3 digits. And the frequency, if you have k digits, then it's 1 over q to the k. And we say that an irrational number is absolutely normal if it's normal in every base q. Okay, some preliminary observations. First of all, no one knows if the the common constants such as pi, e, square root of 2, square root of 3, log 2, log 3, even z of 3. We don't know if any of them are normal number. But we do believe that every irrational algebraic number is normal, such as square root of 2, square root of 3, and any rational algebraic number. But we can't even prove that. We never proved, nobody has been successful in proving any of those rational algebraic number is normal in any base. And what's surprising about normal numbers is there's a lot of them. In fact, Émile Borel, more than a century ago, proved that almost all real numbers with respect to the Beck measure are absolutely normal. So let's look at a quick timeline of the events. Borel introduced that concept in 1909 and proved that almost all real numbers are normal. But it took some 24 years before someone could come up with an explicit normal number. And it's Champernon in 1993, undergraduate student actually. So he just took all the integers and concatenate them together, 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, so forth. And he proved that it's a normal number in base 10. It's not so trivial. Then later, Bisikovich proved that if you take the square, if you concatenate the squares, you do obtain a normal number. So 1, 4, 9, 16, 25, and so forth. And then Erdős and Copeland proved in 1946 that you can concatenate the primes and you do obtain normal number. So they proved that in 1946, and at the same time they proved a much more general number. If you take an increasing sequence of positive integers, such as the primes, for instance, and if the counting function for this sequence is big enough, in a sense that bigger than x to the theta for any theta arbitrarily close to 1, so the primes satisfy that because the counting function is x over log x, then you get normal numbers. So now you get a huge family of normal numbers. So some traditional methods for proving normal numbers. One, for instance, by Nakai and Shiokawa in 1992. If you take a real coefficient of polynomial, and you take the integer parts of the values of the polynomials at integers, then you get a normal number. If you take polynomial with integer coefficients, then you obtain that if you take the primes, values at the primes. There's many approaches using convergence series to create normal numbers. Take Stoneham, this is a very classical one. Write log 2 as a series, like this, the sum n over 2 to the n. As I said before, we don't know, we can't prove that log 2 is a normal number. But what Stoneham did is he considered the truncated series, with just n's when n runs through powers of 3, and then he proved that it was a normal number in base 2. And more generally, Bailey and Crandall, 10 years later, sort of consider a more general case. Take if you we had before the case where b is equal to 2, so we had log 2. Now we take log b over b minus 1, and we get the series. And they proved that if you take the truncated series with just the powers of C, and then if B and C are relatively prime, then you can create this series, which gives you a B normal number. Okay, now let's. The purpose of my talk is to show that we can use the prime factorization of integers to create normal numbers. Okay, where does it come from? Okay, if you look at the normal number, infinite expansion, then take in decimal and base 10 for simplicity. When you look at the expansion, then of course locally it's chaos. That is, if you look like locally set the 100th decimal, just about anything can happen. But globally it's regular. That's the definition. That's the sense of a normal number. Okay, look at now the prime factorization. Okay, let's look at, I take 5 consecutive integer, fairly large number. What happens in the factorization? Well, locally, you know, the relation, the primes of n and n plus 1, besides being of opposite parity, just about anything can happen. But if you take, say, 5 consecutive integers, well, you're sure that at least that exactly one of them will be divisible by 5. At least one will be divisible by 3, at most 2. At least 2 will be even, and so forth. So there is a regularity. Okay, that's a very general observation. But how can you really use this fact, but practically, to create normal numbers? Okay, so let's see. Well, start with one method. If we take, I introduce the concept of disjoint classification of primes. It's very simple. If you take the whole set of primes and divide it in many subintervals, Q subintervals of each positive density, and the sum of the densities is 1, and you allow for another set R, which is possibly finite. You'll see it's very useful. Then you have a disjoint classification of primes. Okay, so an example is just the primes congruent to 1, primes congruent to 3. You get all the primes except 2, and then you do have a disjoint classification of primes. Okay, what's the idea? The general idea is we look at the factorization of an integer n, say p1 up to pr, and we replace each prime by essentially the index of the set to which it belongs. So we associate to p1 up to pr the digits L1 up to LR. It's just the index of the set of primes to which they belong. And then we, with this, will create normal numbers. Okay, just a quick definitions. We say that an expression of the form I1, I2 up to IT, where the ij's are just digits from 0 to q minus 1, is a word. Okay, so it's just a bunch of digits together, so it's a word. And if we reserve the letter capital lambda for the empty word, it's just going to be useful to have that. Okay, the first theorem is that start with the disjoint classification of primes, such that each set of subsets of primes as its fair share of primes in every interval u plus v, where v is no larger than u. And then we introduce this function h of p defined on the primes. It's just, again, like I said, the general idea a few minutes ago, it's just the index j to which that prime belongs. And then we insert the empty word if it's a very exceptional prime that's in that set R, which could be finite. And then we introduce this function t. We define t1 to be the empty word, and then for each integer n bigger than 2, which has then a factorization, but the primes p1 up to pr, we associate hp1, hpr, that's that digit that represents the index of the prime. And then if we concatenate all these values, we obtain a Q normal number. Easy example, get back to those primes congruent to 1 and 3 mod 4. If we look at the sequence T1, T2, and up to infinity, of course, I stop at 15. Well, T1 is the empty word, T2 is the empty word because 2 is in R, and then I get a 1, and then T4 is the empty word again because 4 is 2 to the 2, and so forth. And then if I ignore the lambdas and I concatenate all these digits, I get this number, and it's a binary normal number according to my theorem. Okay, the main tool for creating how do we prove that we obtain normal numbers? Katai and I used an old result of us in, say, 25 years old, 26 years old. We had studied at that time disjoint classification of primes for in a different context, for a different purpose. But then we realized a few years ago that we could use that to create normal numbers. And the result is the following. If you start with a disjoint classification of primes, and we introduce a function that goes to infinity, but very, very slowly, no big over log x, and we take integers a not large compared to x, such that the greatest prime factor of a is bounded by w of x, so the greatest prime factor is very small. Then we have this result. It might be scary to look at this, but it's essentially a generalization or an extension, rather an extension of Selberg-Delange estimate. Remember, for estimating omega of n1 equal k, without this condition that h is a given sequence of digits. So you may recognize if you replace y by x, you get x over log x times log s to the k minus 1 over k minus 1 factorial. But now we have the extension with this function h. And those factors are sort of standard, similar to those that appear in the Selberg-Delange estimate. I just wanted to mention this. It looks scary, but it's not that complicated. Okay, we can generalize that result, start again with the disjoint classification of primes, but then we don't require R to be so small. It can be big. It can be of the set R of primes could be of positive density, and then we still have the same type of result to create a normal number, and you'll understand very well with the example. If you take the congruence mod of 8 of primes, so it's either 1, 3, 5, or 7. If we just consider those congruence classes 1 and 7, ignore the other ones, so we ignore half of the primes roughly, then we can still, because of this extension, this new theorem, we can create again a normal number. It doesn't have to be essentially primes in arithmetic progression. We can have something much more different than that. Take a polynomial with real coefficients, such that at least one of the coefficients is irrational. And then consider two subsets of the interval 0, 1, disjoint intervals, though, of the same length, maybe each one of length 1/4. And then divide all the primes in 3 sets, one for which the fractional part of f of p is in I0, and the other one where the fractional part of f of p is in I1. Remember, these subintervals are disjoint. And then R is the rest of the primes. Well, with this, we can still create a normal number, a binary normal number. Okay, one which I could have started with because it's a simple method, but it occurred to us much later, to Katai and I, is consider the prime factorization of integers. Now so we don't want exponents, but we want all the integers. So allow the primes, the factors to be identical. So we include all the numbers. And then write the n bar for the concatenation of the base q digits of n, and then given an integer n, write the digits of P1, the digits of P2, and the digits of PR, concatenate that, and you obtain a function L of n, which is values are digits. And if you concatenate those values of L2, L3, L4, and so forth, you again obtain a Q normal number. So this one is a more natural way, say, of creating a normal number using the factorization of integers. Okay, a more general case, what's interesting is that you can do exactly the same thing, but this time take a polynomial integer value with integer coefficients, not constant, of course, which is always positive, and put again look at the factorization of integer n, and then instead of having ln to be the digits of P1, digits of P2, then the digits of S of P1, S of P2. So you kind of put a weight on each prime factor, and still again you will obtain a Q normal number. Okay, another interesting thing which happens when you look at the prime factors of integers, if you look at a given integer, say that has at least two distinct prime factors. So forget those integers which are prime powers, in other words. And then what you do is, I want to associate digits to a given integer n. I want to associate k digits. So what do? Is I take the integer part of q times, q is fixed, bigger or equal to 2, of the quotient of the consecutive the logs of the consecutive values, so of the primes. Log of pj over log pj plus 1, of course, is smaller than 1, multiplied by k will not exceed k, will be smaller or equal to k minus 1, because I take the integer parts. So we get digits from 0 to q minus 1. And what's interesting is when you define hn to be the concatenation of these digits, then if you put them all together, you obtain a Q normal number again. So it's interesting, it uses the spaces between, the gaps between the prime factors of an integer. Okay, Sparalinsky raised the question in 2010. He asked, what happens if you take the concatenation of the largest prime factor function, the P2, P3, P4, and so forth? Is it a normal number? So with cat-i, we proved that it is actually. So if you take the Q expansion, base Q expansion of an integer n, write it in this way, and if you concatenate the digits of that integer, or if you do it in reverse order, that's why I put n bar bar. If you start with exactly in reverse order, then if you take a polynomial, again, I go right through to the generalization. So not only we answer Sparalinsky's question, but also we do it even if you put a weight on each large prime factor. And whichever order, then we obtain a Q normal number. And the same, and the proof, okay, the main tool in the proof is old result of Basili and Katai from 1996. If you introduce the function L of n, which is essentially the number of digits of n in base q, take a polynomial again, positive polynomial, positive degree, and take a function ku, which is always bigger than 1. And interestingly, when it goes to infinity, that's when it's interesting. And if you evaluate how many times does a word beta, say 3-digit, digits 4, 5, 6, say, appear in the digit expansion of a number alpha, then Basili and Katai proved that essentially, if you look at how many times, say, a given word beta 1 and a given beta 2 of same length, that's why I write k here, same length appear in the expansion of fp, then they're close most of the time. That's what it says. The number of times where they're far away is very small. And that's the key of the proof of our result. And we have the same result for shifted primes. Exactly the same question that the Sparalinsky raised, but instead of P2, P3, P5, P4, P5, and so forth, we take the prime shifted by 1. And we again, we obtain the same thing. The main tool for this is how does does the largest prime factor of P plus 1 look like? And essentially, it's this result is known. Actually, I think not I think, but I'm sure that in my book with Florian Luca, we have this result. Essentially says that the largest prime factor P plus 1 is the number of times that it's close to the boundary, say, of the interval 1x is small. And so that's what's interesting about this approach that we're doing, creating normal numbers using the prime factorization, is that we have all these tools for analytic number theory that's become very useful, which were not mentioned when in the traditional ways of constructing normal numbers. Okay, with Sparlinski, we use the largest prime factor function. We could have used the smallest prime factor function as well, P of n. Well, you might say, why? How is that? Because when you have an even integer, the smallest prime factor is 2. So we have lots of 2's. Yeah, but remember that we also have other, for some odd integers, you have large small prime factors with maybe hundreds of digits, thousands of digits. So these compensate for the smallest prime factor of an even integer. And we even have more if we take the polynomials, put weights on the smallest prime factor function. And the same thing for shifted primes, with this time with A even, of course, because if A is odd, then we only have 2's in the decimal expansion. Okay, and the more general result with the polynomials. Okay, it's interesting that we can manipulate even more and consider, instead of let me introduce slowly oscillating function. It's just those functions that increase very slowly, like log, double log, or even e to the square root of log. And if you take the expansion, decimal expansion as usual of an integer, and we introduce a different smallest prime factor function. It's just the smallest prime factor which is bigger than eta of n, say log n. See, don't take 2, 3, just take the smallest prime factor which is bigger, say, than log of n, and that will be a q of n. And what if the largest prime factor is smaller than log n? Just put 1, because it doesn't occur very often. And then we create a normal number using this new smallest prime factor function. Okay, the middle prime factor. We can also use other prime factors. Define the middle prime factor as you would expect. If you have 3 prime factors, then you take the middle one, and then you have to be careful if you have an even number. That's okay. That's not the problem. Florian and I proved some time ago that the sum of the reciprocals of the middle prime factor was this formula, and this was sharpened by one of my PhD students, Vincent Ouellet. Any event, it did create some buzz in the literature, so we figured maybe we can use this to create normal numbers. First, observe that that essentially the log of Pn, the normal order is 1/2 log x. But we use this result here, and using this, we can prove that if you concatenate the middle prime factors of integers, you obtain a Q-normal number. Finally, let's look at the number of distinct prime factor function. One would be tempted to say, what if we concatenate the various values of omega of n in the hope of creating a normal number? Well, it won't work, because this is not a normal. We can prove that. And essentially, why is it? Is that if you look at all the integers up to an interval 1x, most of them will have log x factors, so say r factor. And so, except for a negligible number of integers, we always have r log x essentially. So that means we don't have a normal number because every value of omega of n should occur the same number of times essentially. Okay, but what we do is we consider how far it is from the its normal order. So we consider this function a of n to be omega n minus log n. And this way, by concatenating the n's, we create a normal number, and we have the same type of results for shifted primes. Okay, I've finished with this very rapidly. There are so many conjectures. I just name one. If you take the value of omega of n mod q for a fixed q, think of the binary one, say you get 0, 1. And the same thing with big omega. I forgot to say, big omega is essentially the number of prime factors, but counting multiplicity. And then if you look at the concatenation of these epsilon 1, epsilon 2, and so forth, and the same thing for the big omega function. Or another one, if you take mod q, the value of omega of n, Pn plus 1, so the shifted primes, then we conjecture that in all cases, we obtain a Q normal number. It's sure that it's true, but it seems to be very difficult. In fact, if you look at the very particular case where Q equals 2, and you take delta, which is this omega of n here, it's essentially the Challa conjecture, which I won't state here, but which Helfgott will talk about tomorrow in his talk. So that's it. Thank you very much. By the way, all my papers are on my website, so you can see I have almost 20 papers with cation on normal numbers, and they're all there, so you can all get all the proofs. So thank you for your attention.